Welcome to Chapter 4 on rational functions, and in this video we are going to introduce and define a rational function and revisit domain briefly. What I have here is a rational function, and basically a rational function is when we have a polynomial up top and one down below. It doesn't technically have to have x in the denominator, but when it does, that's usually what we call a rational function, which we'll define in a minute. Now we can see here that in our denominator we have x squared minus 9, and as we know, the issues here that would make our denominator 0 would be when x is 3 and when x is negative 3. However, if we take a look at our rational function, we can see that there's really only a vertical asymptote when x is negative 3 and not positive 3. And let's just explore a little bit why this is. If we factor the denominator, it's a difference of squares, so we'll have x minus 3 and x plus 3. That's what x squared minus 9 will factor into. And so we can clearly tell that the two values that make the denominator 0 are positive 3 and negative 3, that we've already said. However, we can actually cancel the x plus 3's since they're common factors, x minus 3's, since they're common factors top to bottom. And we can simplify, and this rational function becomes 1 over x plus 3. Showing us that the only issue is really when x is negative 3. Now, x equals positive 3 is still an issue, but it's not one that creates a vertical asymptote like we see here. So we're going to be exploring these types of rational functions and what makes a vertical asymptote, what makes a hole in the graph, and just kind of seeing how these look on Desmos or our graphing calculator. They look pretty cool. We can see that we have different asymptotes. We have the graph approaching the x-axis here on both sides, and we'll discover how to find all of those things algebraically. Let's define mathematically a rational function. A rational function is any function of the form f of x equals p of x over q of x, where p of x and q of x are just polynomial functions. We just finished studying Chapter 3, which is all about polynomial functions, and a polynomial function can look like just p of x equals like 2, right? Or it can be like 2x to the 5th minus x to the 4th plus 7x minus 4, or something like that. So polynomial functions can really look like a lot of different things. And what if q of x was just 1? That would just mean that a polynomial function, p of x, is also a rational function. However, rational functions are not always polynomial functions since q of x might have x in it. So a lot of times we will see rational functions with x also in the denominator, which, since our denominator cannot equal 0, can sometimes cause some issues. Let's explore what those issues might be. A rational function might have asymptotes, whether they be vertical, horizontal, or slant, and we are not going to get into slant asymptotes in this course, but you might see them in the future. A rational function might also have a hole in its graph, which is very small and we cannot actually capture on Desmos or any graphing utility that we use. And a rational function most certainly can have restrictions on its domain, since whenever we have x in a denominator, we have to watch out, and we definitely will have restrictions on the domain because we don't want our denominator to equal 0. We are going to revisit domain. It's something that we talked about at the start of the year, and I'm just going to do a brief review on it with 4 examples. We want to find the domain of each rational function. Numbers 1 and 2 look very similar. As you can see, I just flipped the numerator and denominator. If we look at number 1, this does not actually have to be written as a fraction. If you take a look, because it only has a monomial as its denominator, a single term, we can actually rewrite it as 4x over 4, which is just x, and then minus 3 over 4. Now, we can rewrite it this way. You don't have to. I'm just showing you that it doesn't necessarily have to look like a fraction with x in the denominator. It really just is a polynomial function. And since x is not in the denominator here at all, we do not have any restrictions on our domain. Therefore, our domain is all real numbers, and in interval notation, we know it looks like this. In number 2, because we flipped, we cannot break up this into 2 different fractions because we do not have a single term in the denominator. We now have a binomial. Now, we do have a restriction on this domain because we have an x in the denominator. So what we're going to do is we're going to take our denominator and set it equal to 0, or you can write not equal to 0, whatever you prefer visually. And then when we add 3 and divide by 4, we see that x cannot equal 3/4. That is the restriction on our domain, because if x equaled 3/4, our denominator would be 0. So our domain is from negative infinity to 3/4, but not including 3/4, union 3/4, but not including it, all the way up to infinity. So as you recall, that is how we restrict a number on our domain. Let's take a look at number 3. This one's a little bit more complex looking. G of x is most definitely a rational function, and we can see that the denominator has an x in it. Therefore, there are going to be at least one value, in this case 2 values, that make the denominator 0 because our denominator is a quadratic, whereas in number 2 our denominator was linear, so there was only one restriction on the domain. Here we're going to have 2. So what we're going to do is factor our denominator. We'll first set it equal or n equal to 0, since it can equal 0. And there are definitely 2 ways to go about solving this. I'm going to encourage you to factor because we're not always going to be able to directly solve for x. So I'm going to factor the GCF out, which is 2, and we'll be left with x squared minus 9. And then this is a difference of squares inside. X squared minus 9 factors into x minus 3 and x plus 3. So we have 3 factors. And again, I'm only saying n equal to 0. You could easily say equal to 0. It doesn't really matter. I just want to hammer the point that we do not want these numbers in our domain. There are restrictions. They're like not good values. I don't want to say the word negative in math, but we do have 3 factors here, a 2, an x minus 3, and an x plus 3. The 2 is not going to provide us any solutions because there's no variable in that factor. So we're going to have 2 solutions here. When we set x minus 3 to 0, we'll say that x cannot be 3. And then when we set x plus 3, n equal to 0, we'll have x cannot equal negative 3. Those are the restrictions on our domain, and we're going to write it in the same way that we wrote number 2. So we're going to start at negative infinity and go to our first value, which is negative 3, and skip over it. Then we're going to start at that value again and go to our other value we want to skip, which is 3, and then go from that value all the way to infinity. Because we have 2 restrictions on our domain, we're going to actually have 3 intervals that our domain is written in. In problem number 4, we want to take our denominator again and set it to 0 to find the restrictions on our domain. And in this case, I'll show you I can just put equals 0. It doesn't matter. We're doing the same thing. And I can see that we again have a GCF. This time it's 3. So I'm going to factor the 3 out. What we have left on the inside is a quadratic trinomial with a being 1. And so we want 2 numbers that multiply to a times c, which is negative 2, that add to negative 1, our b value. This is factorable, and so we'll get x minus 2 and x plus 1. If you're ever unsure if you factored correctly, you can just multiply through, since factoring is just reverse multiplication. Again, we're going to set each of our 2 factors that have x in them equal to 0. We do technically have 3 total factors, but the 3 out front, the GCF, since it doesn't contain a variable, will not produce a solution. So we're going to have x equals 2 and x equals negative 1. Now those are restrictions on our domain, so I could easily write it this way too, if you'd like, however you want to express the domain. But we want to write it in interval notation. So our domain is all real numbers except negative 1 and positive 2. So we jump over those values from negative infinity to infinity. Now if you notice in problem number 3, we had an x minus 3 in our numerator, and that was also one of the factors in our denominator. Those 2 things can cancel, but it's not going to affect our domain at all. We're going to explore canceling from factors from top to bottom in the following 2 videos when talking about the difference between vertical asymptotes and holes in our graph.